Dear MATLAB lovers, welcome to this session. The scenario given to us that we must solve in MATLAB says that an engineer is analyzing the dynamic response of a simply supported beam subjected to harmonic load. The displacement of the beam varies along its length, and the engineer wants to visualize the vibration at 3 points. At x is equal to 0.25 times the length of the beam. At another point, x is equal to 0.5 times the length of the beam, and at another point that is at 3/4 of the length. Okay, so the displacements can be approximated by sine waves with different amplitudes, frequencies, and phase shifts. The tasks given to us are that we are to create a time vector from 0 to 5 seconds with a time step of 0.01 seconds. We are to take displacement as a function of time, and we have y, which is a function of time, equivalent to a, which is amplitude, times sine of 2 pi ft plus phi, where a is the amplitude and the displacement. This is the maximum displacement in meters. F is the frequency in hertz. Phi is the phase shift in radians, and T is the time in seconds. 2. We are to define the displacement at 3 points using the following equations. Remember, we have been given the x values, okay, and we have been given the different points in terms of displacement. So one is that we are to look at the displacement y1 of t equivalent to 0.5 sine 2 pi, so where the frequencies is 1 hertz and there is no angle shift, no phase shift. Then another one is 1 times sine of 2 pi 1.2 t, and we have a phase shift of 0.2 radians. Then next one is 0.8 times sine of 2 pi times 0.8 times t with a phase shift of negative 0.3. So this is delayed, this is delayed, this is faster, and this is the slowest because it has no phase shift. Plot the displacements using the subplots. Subplot 1, we have x is equal to, that is where we have x is equal to 0.25 L. The one to analyze the response at x is equal to 0.5 L. Another one to show the response at 0.75 L. So we are to add a super title for the figure, and it should be reading beam vibration response at different points. We are to label our axes appropriately and add grid lines. Now, deliverables in this scenario is to have a MATLAB script implementing the scenario and the figure showing the 3 subplots. Let's go to MATLAB. We are using MATLAB 2010. So let's solve this problem. So first of all, when we go back, we see we are to plot, but now we must create first of all a vector to initialize the values of time from 0 to 5 with a step size of 0.01. Okay, so before we do all that, we could say this is a code for beam vibration, for vibration response analysis, and then we want to see we want to see displacements or displacement at 3 points along the beam. So this beam is under, you can say the beam is under harmonic, a harmonic load. Okay, so let's continue. We can now create maybe some space. We go down. So what we are going to do is to clear the command window. Yeah. Then we clear the workspace and we close all open MATLAB windows. So whether they are figures for plots from other sessions, all of them should close, and it's only the figures from this code that must be open the moment we run. So we are going to create sections of the code, and this is how we create the sections. We are going to use double what? We use the double percentage sign to create a section. So a section helps us to create a code, a section of a code that does a particular purpose and which we can run independently later on without running the rest of the script or the rest of the code in this file. So we are going to create number 1, creating a time vector. So this is what we do. We are going to say t is equal to, we said it is ranging from 0 to 5, but with a step size of 0.01. So let's go. The moment we create that, this means we are having step size of 0.01. Let's go. Next, we are going to define displacement. So that section is done. We can say number 2 is to define the displacement at 3 points. So that means I will have y1, which is equivalent to, we said 0.5 according to what is given. So we multiply by sine, of 2 times pi times 1 times t. And this is true at x is equal to 0.25 times L. We can suppress this, then we copy this 3 times. Then we call this y2 and this y3. So this is we are supposed to make this 1.2, and then we add 0.2. That is the phase shift. Then here we are supposed to subtract 0.3, but this is supposed to be 0.8. So we can clear this. So this is at 0.5, this is at 0.75. Next is let's create another section, number 3, where we upload using subplots. So we are going to initialize here. We say we want to create a figure, and that figure must have subplots, and the subplot is going to be a 3 by 1. Okay, so that means a 3 by 1. I'm saying we are going to have these subplots are going to be arranged in form of a matrix. So you have one on top, another one down. So you have 3 rows and 1 column. So that's why we say it is 3 by 1, but in position number 1 we are going to put this. So we are going to say plot we have to plot x, we have to plot t against y1, or we plot y1 against x. Yes, and we want this to be in red, and we want it to have a line width. This is supposed to be declared as a string. Line width, we can say 1.5. If you like, can add more. Then we say title, and this is going to be, we can call it displacement at x is equal to 0.25 L. Now next, we are supposed to also label the axes. So we shall label the x-axis, and we call it, can say this is time in seconds. You can have it as small s. We say y label. This is going to be obviously displacement in meters. Then, since they said we need the grids, we shall say grid on. So we are going to do 3 of them. So we have 1, which is going to go to position number 2. Then this is going to be for 0.5 L, and we can make this K. We make, that is for black, we make this B for blue. So this is going to be at 0.75, and then this is going to be plot. This is the y. Let's make this y3. We make this y2. The rest is okay. Let's just create space here, and then next, this is supposed to be number 3. Yeah, so it is a 3 by 1 matrix of figures, but we have figure 1, we have figure 2, and figure 3. Can remove this since there are many. We create a space here. So This is y2, and that's all. The next one is maybe we can, since this is blue, this is k, that is red, it's okay. Now the next one is to add the super title. So we use SG title. So SG title, we are told that this is supposed to be this. So let's copy beam vibration response at different points. So we can put it there. So let's first now save this. Let's save. We call it beam vibration analysis. If you don't put these underscores and you leave space, it shan't allow to be saved with the spaces. But the only way to make it with the spaces is to add underscores. So let's run this and we see. So this is basically how it looks like. Now let's first look at we look at graph by graph. You can see that this graph is ahead of the rest of these other graphs. So that's why we have the positive phase shift puts it ahead of the rest. This one is a little bit delayed, and it also has an issue in one way or the other. Let's first go back and look at the amplitudes. Okay, so this is supposed to be, they were given to us. I remember these graphs, these were given to us. So let's go and edit. Yeah, they were here, 0.5. So let's go to our code. We had 0.5, then we had 1.0, 1.0, and then lastly we had 0.8. So we can now analyze this. We can see that this one's response is a little bit slower. This is faster than the rest of them. And since this one has no phase shift, it is a little bit also faster than this. But again, when it was delayed with a negative phase shift, it also became slower. So we can tell that this response gives us a graph in which the phase is ahead of the rest of others. Probably we can say that the displacement here, the displacement in here is small. We have a small amplitude because we have a mild, with a small amplitude, we can get mild vibration. See, the amplitude for this is 1, and then we are getting the strongest vibration. But this other one, we have also a medium, because you see this is between 0.5 and 1. So it is at 0.8, and this one has a medium amplitude, and it has a slower vibration than this. Yeah, so we can tell that when a beam is subjected to a dynamic load, like a harmonic force, impact, or moving load, it vibrates. And that's very important for us to see from these graphs. The displacement over time at any point along the beam can be described as a time-dependent function. and this is often sinusoidal, like we have demonstrated in this in these graphs. So maybe we can add another optional plot where we overlay these graphs onto one figure. So let's go and create another section. Number 4, we say overlay of the 3 responses on the same graph. What we are going to do here is to plot. We are going to first initialize our figure. Yes. Sorry, we are supposed to take this somewhere below here. Yeah. So now we are going to plot t against y1, and then we can actually just copy this, put it here, we put it there. So we just change here, and then we can call this R, we call this K, and we call this blue. Yes. So what next is to put the X label and the Y label. So we say X label, Y label, and then we can talk about the title. And we say this is an overlay of the 3 responses on the same graph. We can say legend, we want to show the key of the graph of the plot. We will declare it as a string. So we'll have x is equal to 0.25 m. Yeah, we want many of them in the same legend. So we're going to bring this x is equal to 0.5. This is supposed to be a string. We have another one. This is 7. Okay, so we want the grids on. Okay, so the moment we run, let's see. So when we plotted this, we should say hold on, so that now the rest can be on the same plot. So we can see this is exactly how we needed the output to be according to the inputs to the system. Because we remember we had the beam and this beam we are giving it a harmonic load. So the response of the vibrations is being displayed on the graph. So you can see that where you have more frequency, where you have more frequency, then you have a faster response. Okay, and that's why you can see that for this of 0.5, you can see it is ahead of others because for it even has a positive phase shift. Then this is slower because it is having a negative phase shift. So you can have these plots, first of all, one on where you have everything on the same graph, and then another one where you have the rest are subplots. So this is the 3 by 1. So there are 3 rows and 1 column. So 1 occupies position number 1. So that is the one that we we put later. Then this is now the 3 by 1 stroke 2. Comma 3. This is the 3 by 1 on the 3rd position. So this is how you can explain the 3 by 1 by 3, the 3 by 1 by 2, and the 3 by 1 by 1. Just tell you that the last figure is just giving the position of the subplot. So ladies and gentlemen, this is how we can be able to solve this problem. Maybe more insights about this. We can see that this mimics how let's bring it here. This mimics how a beam reacts differently along its length under a dynamic load. And this type of plot is very useful. It is called the time history response of the beam. Engineers can utilize it to check the maximum displacement, vibrational frequency, and phase differences along the beam. So they can use it to design supports, damping, and in even selecting of materials that the vibration, that the materials for designing the beam that will withstand particular levels of vibrations. So this is how the problem has been solved. So remember that the file for this code is going to be in the description. So endeavor to check in the description to be able to pick that file of the code, and then you go and experiment. Thank you.